All right, we're going to do sort of a loose end. I want to talk about section 14.2. And this is about limits and continuity. And so this is, it's a section in the book that we don't need to do, but it's on the syllabus, and there's some things here you should know. Okay, so this is done before partial derivatives because we have a function of two variables or more. What the partial derivative is really defined to be a limit, just like it is in a single variable, right? So just recall that f prime of, say, x is the limit, say h goes to 0, of f of x plus h minus f of x divided by h, right? So that's the definition of the limit. And we've talked about when we have a variable of a function of two variables, we just keep the y constant. So the obvious thing to do to get x derivative would be df, or let's do the subscript notation, is fx of xy. So this is the x derivative of the function xy. Is going to be the limit as h goes to 0 of f of x plus h, comma y minus f of xy. So we fix the y divided by h. And similarly, the y derivative, fy of xy, is going to be the same thing. I'll write it down. Limit h goes to 0, f of x, and then here we move the y a bit, f of xy divided by h. Okay, so here's how we define partial derivatives. So partial derivatives are defined using limits of functions of say two or more variables, right? Okay, so what we want to talk about limits of functions of two or more variables. That's what we need to talk about. Okay, and we haven't talked about it because mostly things behave the way you expect. We are able to compute a bunch of partial derivatives, and we don't really have to worry about what it really means. But there is an issue that you should be aware of that can happen. Okay, so somebody just explained that immediately. Is the problem is what can happen is you can approach a limit from different directions when you have more dimensions available, and those can give different answers. Okay, so it's possible to approach the limit from different directions and this will give different answers which will tell you that the limit does not exist. Okay, and that's the thing that's different in two dimensions from, or the higher dimension than one dimension. With different directions, giving different answers means the limit does not exist. Okay, so let's look at maybe some examples right away. So I'm just going to, the one that the book looks is a good one, I think. So we'll just look at this. Okay, so it's sort of very clear. Starting example, so let's just start with that. So let's look at the limit of, say, xy goes to 0. So we have two numbers going to 0 of f of xy, or let's do a particular function, x squared minus y squared over x squared plus y squared. Okay, so the answer, it's this case here, does not exist. So why? The y is because we can get different things, right? So let's set y equals 0. Then here, then what do we get? We get x squared over x squared. So we can look at the limit, and that's equal to 1. Right? So if y equals 0, our limit is 1. But if we set x equals 0, and we look at the limit, say y goes to 0, of y minus y squared over y squared, we get negative 1. Okay, so x equals 0 gives us a different limit. Okay, so in the picture is in the, we've got our xy plane here. And this function is going to take all different kinds of values. But the issue is when we're traveling here, we get one value. We're traveling here, approaching here, we get a different value. So, and we can try other things too. We could say, let's say x squared equals y squared is equal to some, x is y is t squared. Let's say x is y is t, right? So here we're looking at this line here. And then what's the limit t goes to 0? Well, we're going to get t squared minus t squared over t squared plus t squared. So that's going to be 0. Right? So along this line, we're getting 0. Along x, y is 0. We get 1. And over here, we get minus 1. So we get all different kinds of values. And so the limit does not exist. It doesn't make any sense. Okay, and so in that situation, there's we can't define the limit. And so that's really what happens new in higher dimensions. And so in the book, they do the other example. You have sine the limit as x and y both go to 0 of sine of x squared plus y squared over x squared plus y squared. And here, what happens is it doesn't matter how you approach, how they go to 0. You're always going to get 1. And so this has limit 1. Okay, and so let's see. So, and I'll mention, so the limit satisfies a bunch of good properties, but let's maybe mention just a few of these. So, so the limit xy goes to ab of f of xy equals f of ab. This is the same. It's the definition of being f is the function f of xy is continuous at the point AB. Okay, so that's the definition. We won't really need to use it that much, but that's how we define continuous. All right. And of course, we can do this with more variables. There's not a whole lot to say about this section, so I don't want to go into a huge lot of detail. It's going to be a pretty short video. It's just sort of a loose end I want to tie up that we're supposed to cover, but we didn't. And the reason we didn't is it's not super important. It's something you should be aware of. There's an issue, you know, if you're plugging things that don't make sense, there is a limit. There's this problem that it can be different values as you come from different directions. So let's take some examples here. Yeah, so here's an example. It says find the limit. Okay. Yeah, so so a lot of these are kind of boring because you just plug it in. Let's try maybe, here's one. It's maybe a little more interesting. The limit. So you know, if it's just continuous functions, you just plug it in and that's it. Here's one: x squared y cubed minus x cubed y squared over x squared minus y squared. Okay, so if you evaluate, you get 0. You get 0 over 0. Okay, so that's not going to work, right? But what can we do with this? Well, the fact that we're getting, if x equals y, we always get 0 means we can factor that out here, right? So x equals y, that implies we get 0 over 0, right? That means x minus y is a factor of both, okay? So this expression here, x squared y cubed minus x cubed y squared divided by, I only factor the bottom right away because that's a difference of squares. That's easy to factor. Oops. X plus y, right? And now what I'm claiming is we'll be able to factor the top into x minus y times something. So let's just try and see what we would get. So we write x minus y, x plus y. Okay. Let's see. So we probably need an xy cubed, it looks like. Right, and that will give us the right thing on the front. And then we'll have an x y to the fourth. So there'll be something, it'll be a little bit long here. At the end, we're going to need oh yeah, well, let me just factor out the obvious thing to factor. X squared, yeah, just making this more complicated. X squared, y squared factors out of that, and that leaves a y minus x, which is the negative of that. So, okay, so we have the limit xy goes to 1, 1 of this expression. We can factor both. This is a common thing you do when you evaluate limits, right? You want to factor them. I don't need that line there. Right, so we get, well, they can be negative of each other, but that's okay. We're going to have y minus x squared, y squared, x minus y, x plus y, right? These guys are going to cancel, give me a minus 1, as long as I'm not evaluating where x equals y. So this is going to equal x squared, y squared, the limit of x squared, y squared over x plus y. And now we can just plug in, right? So we're going to get a 1 over 2. And that's the answer. Okay, so that's one example, just evaluating a limit. And let's do one where it does not exist. All right, let's look at this one. So here's another example. Let's look at the limit. So I don't know, well, we'll find out in a second if this exists or not. Xy goes to 1, 2 of, I don't know, that one's going to exist. Let's try to find one doesn't, I don't think exists. Yeah, let's do this one. Xy goes to yeah, let's go to 2, 3 of 3x minus 2y divided by 4x squared minus y squared. Okay, and so I'm claiming this one won't exist. The answer is does not exist. And how do we do that? Well, what we want to do is we want to find two parameterizations of curves in the plane that give different limits. Okay, so what we want to do is we want to check this, we're going to set up an x of t and a y of t. And that's going to give us something. So a simple example is like, say, let's make the top 0. Okay, so to make the top 0, I can say this is 2 t and this is 3t, right? So that's going to be our x of t, y of t. And then we want to compute the limit as t goes to, we want to get 1 to get the point 2, 3. We'll find the limit as t goes to 1 of this function now with this parameterization. So 3x minus 2y over 4 squared minus 4y squared. So this is going to be the limit t goes to 1 of 6t minus 6t divided by, on the bottom we're going to have 4 times 4 is 16t minus 3 squared is 9, 9t squared. So that's going to be the limit t goes to 0, or to 1, of 0 divided by well, 16 minus 9 is 7t squared, and so that's certainly 0. All right, that's all well and good. Now, what we want to do is evaluate this at something else, right? So that's one parameterization. So we're going to find a different parameterization where we don't get 0. And so there's lots of possibilities. We might as well say x equals y. Okay, so that'll be x of t is t, y of t is t. Right? If the limit exists, we'll get the same answer no matter how we do this. So now we want to compute the limit t goes to 1, so that's one computation. The next one is the limit t goes to 1. This will be 3t minus 2t divided by x squared will be 4t squared minus t squared. Okay, so that's going to be 3t, it's going to be t on top, so it's going to be the limit t goes to 1 of t divided by, looks like 3t squared. Okay, and now we can just plug in, and it's going to be 1 over 3, and that's not, these are not the same, right? They're not equal. Okay, so 0 is not 1/3, and implies the limit does not exist. Okay, and that's enough. That's 2 examples, and that's really kind of shows you the kind of behavior we get for limits. And you should know just a little bit about limits in higher dimensions, and you should know this issue about approaching from different directions, and this is how derivatives are defined. All right, well, that's it.